Hello, everybody. Hopefully, you guys are staying safe and healthy out there, and you're not too bored in your self-isolation. I'm just walking around this empty classroom, which feels a little bit more surreal every day, but that's okay. We'll just keep moving here. Hopefully, you have already finished everything for our previous unit on solving equalities and inequalities. If you have any questions with any of that, please let me know. So we are now moving on into the next unit, radicals and absolute value functions. So this is the notebook. This is what I'm going to use to go through. I put the printed copy and all of my notes up online for you, so you can kind of use that as a reference. I wouldn't worry too much about you guys creating your own or following along with the notes. Just look at my copy of the notes and kind of look at the video, and then if you have any questions, email me or just put them in the comment section below this video. All right. So the first section of this unit is looking at reviewing radicals. So let's take a quick look at what a radical is, and let's see what we remember from Math 10C. So in mathematics, radicals are written in the form the square root or n root of a. Sorry, which is really weird to say. So n exists as a natural number, so that has to be like a whole number, 1, 2, 3, 4, 5, 6, 7, 8, 9. And a is any real number that the radical can be defined for. Now, when you say in those terms, it really doesn't make sense. But most of the time when we're using radicals, we are using them to represent some sort of irrational number, right? Because, for example, like if I take the square root of 2 and I put that on my calculator, I get 1.414231, blah, 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 right? I get this irrational, randomly trailing decimal. I don't want to round that because if I keep rounding in subsequent calculations, I'm going to get further and further away from the correct answer. So rather than writing it as that, what I can do for consecutive computations is I just keep writing and using the square root of 2. And so that's what a radical is. We should also recall the following parts of a radical. So right, this entire thing is considered a radical, but there are some different parts here. The first part is what's out front here, right? This 5. That 5 is called the coefficient of the radical. The same way, if I had 4x cubed, here 4 is the coefficient. It's just that number out front. The 3 is what we call the index. And the index tells us what root we are taking. Remember, when I said, we talk about root 2, the invisible index here is a 2. We don't ever take the 1th root of something, right? We're always taking the square root. So if there is no visible index, the index will equal 2, which means we're taking the square root. So we could take a square root, we could take a 3rd root or a cube root, we could take the 4th root, we could take the 5th root, 6th root, etc. Okay? So that just tells us what root we're taking. Obviously, this is my radical sign or my root sign, depending on where you're looking. And the number underneath the root sign here is what we call the radicand. And that's what we're taking the root of. So some basic terminology there. The last thing that you should remember in terms of terminology is the difference between an entire and a mixed radical. And I'm going to mess these names up over and over again through this video, so I apologize right now. An entire radical is when all of the numbers are under the root sign. So, if I look at this and this, well, which one is the entire radical? If the entire radical is when all numbers are underneath the root sign. That would be this right here. This is an entire radical. This entire radical is actually equivalent to this other radical right here. And that radical right there is what we call a mixed radical. So mixed radicals have a coefficient out front other than 1, because technically, I could have a 1 here, but it doesn't really do anything. And so when I look at a mixed radical, generally we have like a number or maybe some letters as a coefficient, and I also have numbers and letters underneath my root sign. So this is considered a mixed radical. Okay, and these two forms are equivalent. They are just written or they look different. And what you should remember from Math 10C is how to go back and forth between these two types of radicals. So that's what I'm going to review here quickly. So creating an entire radical. And so an entire radical, remember, means all of the numbers underneath that root sign. So to do that, to create an entire radical, we bring the coefficient under the radical sign to the power of the index. So looking at this example A, 3 root 15, I would take the 3 and bring it underneath the root sign. So 15 times 3 to the power of the index. Now there is no index there that we can see, so need to remember that that invisible index is a 2. So that would just be 15 times 3 squared. So 15 times 9 is 135. And all I do, right, is I simplify these. I don't need to put it in my calculator underneath the root sign. I would only use that to verify because this is an irrational number. So I don't want to put it in on my calculator. I want to leave it as a radical. So I can verify that I did this right because I'll just go to my calculator and say, okay, what's 3 root 15? That's a mixed radical, and that's 11.6. Is that equivalent to our entire radical of 135? Yeah. Both of those decimals are irrational numbers, and they are identical. So our mixed radical and our entire radical are the same. So I know that I converted from one form to the other correctly. If you want to take a second and pause the video and try B, I would like you to try that right now. Okay, so hopefully you tried that. What you should do is take the 5, bring it underneath the root sign. So this is 10 times 5 to the power of the index. So 10 times 5 squared is 25. So 10 times 25 is the square root of 250. And if you type in both of those radicals, they should both equal about 15.81. 15.81, some irrational number, but they're equivalent, so we know that we have converted correctly. The next question here, C, is 6 cube root 12. The one thing to look for here is this is actually this, not this. Right? Those are two completely different things. So if you're seeing this and they're really close together, what's more likely happening is this is the index, not the exponent on 6, which is where some people will mess up. So to convert this mixed radical into an entire radical, I'm going to take the 6 and bring it underneath my root sign. So this is still the cube root. Do not change what root you're taking. So that's still going to be the cube root of 12 times 6 to the power of the index, which is 3. So the cube root of 12 times 6 cubed is 2,592. And then if I'm unsure, it's a cube root, maybe I did it wrong, let's just go check that those are equivalent. So I'll type in my mixed and my entire radical. So remember when you're calculating the cube root of something, you can just go to that math button. So I'll go math down to the cube root of 2,592. That's my entire radical. So that's the irrational number it's equivalent to. And I want to see that that's equivalent to 6 times the cube root of 12. And those are equivalent so that I know I've converted back and forth between those forms correctly. Sorry. I have a habit of circling my answers. Okay. Last question is 5b. So again, remember this is 5b times the cube root of a b squared. So to solve this question, I'm going to take 5b and bring it underneath the root sign. So my index stays as a 3ab squared. I haven't touched that, so I'll leave it, times by 5b all to the power of 3. And I put that in brackets because the entire thing needs to be put to the exponent, not just one of them. Now, in this type of question, we have to remember exponent laws. And so exponent laws here that I would use is power of a power. Because this is a monomial, I can distribute that exponent and multiply it to the other exponents that are here. So this is the cube root of AB squared times by 5 to the power of 3 is 125. And b to the power of 3 is just b cubed. So I'll leave it as that. I can't leave that as my final answer because I want this as simplified as possible. So my final answer will always usually look like the number first, so 125, or my coefficient. Not really coefficient because it's not up front, but underneath here. A, and then b squared times b3. You have to remember your exponent laws, which say if you have the same base and you're multiplying, you add those exponents together. So that would be b to the power of 5. Okay. It's a little harder to verify those type of questions because I have multiple variables. I can't really graph it, but I could technically choose some arbitrary value for A and B and see if they're equivalent that way. If that makes sense, great. If not, you want me to explain that further, fire me a message and I can do that. All right, next part then is reversing this process. So we need to undo, now like work backwards here. How do I go from this entire radical to a mixed radical? And so we call that simplifying radicals, but really we're taking an entire radical and making it into a mixed radical. What we want to do is we need to remove the largest perfect number of the index from the radicand. Now, there's a few different ways that you can kind of approach this. So I'm going to kind of look at it in like the longest way to do it, and then we'll start looking at some shortcuts. So basically what I'm going to do here is look at this, the square root of 60. I need to break that up into some factors, and the factors have to be some sort of perfect number of the index. So because the index is 2 here, I'm looking for factors that are perfect squares. First thing I'm going to do is just list all of the factors of 60. 1 times 60, 2 times 30, 4 times 15, 5 times 12, and 6 times 10. Those are all of the factors of 60. Now I need to see out of those factors, which of them have a perfect square as one of the factors. Well, 1 is technically a perfect square, but I'm not ever going to use that because it's not simplifying. 2 and 30, neither of those are perfect squares. 4 and 15, well, 4 is a perfect square, so I'll leave that there. 5 times 12, neither of those are perfect squares, and 6 times 10. So in this example, there's only one factor, or one number, or one set of factors that are a perfect square of 60. So I will break 60 up into 4 times 15. I can do that because I haven't changed anything. Rather than saying 60, I just put it as 4 times 15. Those are still equivalent. I haven't changed anything. I have preserved equality, so that's okay. Then what I can do is really what I'm doing is splitting this up now. So square root of 4 times the square root of 15. Again, I haven't changed anything. I just changed the way it looked. So rather than saying it's getting the root taken all together, they're being taken individually. Well, the square root of 4 is a perfect square. The square root of 4 is 2. And the square root of 15 is like some ugly irrational number on my calculator. So I'm going to leave it as 15. And hopefully those two are equivalent. And I can always check, right? I'll just go the square root of 60 gives me 7.745, and 2 root 15 gives me 7.745. So those are equivalent, which means I've successfully converted from this entire to this mixed. Okay, B, 180. So if I wanted to go and write out all of the factors are 180, there's going to be quite a bit. So rather than writing out all of the factors like I did here, what I could do is just divide 180 by perfect squares. Because we're just trying to find the largest perfect square of the index. So perfect squares are like 1. So 1 times 180, but I'm not going to use that anyways because it's not simplifying. The next perfect square is 4. So 4 times 45 is equal to 180. After 4, the next perfect square is 9. So 9 times 20 gives me 180. 16 is also another perfect square, but that doesn't divide evenly into 180. 25 is my next perfect square, which doesn't divide evenly into 180. After 25, it's 6 squared, so 36. So 36 times 5 is 180. 180, I could go divide by 49, which now if I look, that's an irrational number, and it's less than some of these numbers that are here. So I know that I found all of the perfect numbers or perfect factors of my index. So then out of these sets of numbers, 4, 9, and 36 are all of those sets of factors. I'm looking at just the perfect squares. So 4, 9, 36. But my step here says I want to use the largest perfect number of the index. So 36 is the largest perfect square. So I'm not going to use either one of those. So I'm going to use 36 and 5. The reason being is I want to keep my answers as simple as possible. It's the same way in, like, you know, when you do fractions, you reduce your fractions. We want to do that with radicals as well. So I could split this up into the square root of 36 times the square root of 5. Well, if I split that up, I'm really just taking the square root of 36 times that by the square root of 5. And I know the square root of 36 is a perfect square. It's 6. 6 root 5. And there's my answer. And those should be equivalent if I check. If you can look at this and just jump right here, that's great. I'm fine with you doing that. Because really, when I'm doing this, and once I find the factors, I'm just going to say to myself when I do this question, I don't write all this down. I just say, well, 36 and 5 multiply to 180. The square root of 36 is 6, and root 5 is my irrational number. So that's how I would do it as kind of a shortcut. Okay, the next one is how to convert the cube root of 120 into a mixed radical. Now, this is a little bit different because we are no longer looking for perfect squares. We are looking for perfect cubes. And so if you remember perfect cubes, 1 times 1 times 1 is 1, 2 times 2 times 2 is 8, 3 times 3 times 3 is 27, 4 times 4 times 4 is 64, 5 times 5 times 5 is 125. So I need a factor, a set of factors that has at least one of those numbers in this to convert that into a mixed radical. So then what I'll do, if you're not sure, if you can't see, off the top of my head which ones divide in, I could write out all the factors. So all the factors of 120, 1 times 120, 2 times 60, 3 times 40, 4 times 30, 5 times 24, 6 times 20, 8 times 15, and 10 times 12. A lot of factors. That's why it's easier if you just look for the perfect numbers of the index. But either way. So then I got to go look for one of these numbers here. Well, this isn't a perfect cube. 2 and 60, neither of those are perfect cubes. 3 and 40, neither of those are perfect cubes. 4 and 30, neither of those are perfect cubes. 5 and 25, neither of those are perfect cubes. 6 and 20, neither of those are perfect cubes. 8 and 15, 8's a perfect cube. And then 10 and 12, neither of those are perfect cubes. So I would take those, because that's the only one, let alone the largest one, and put it in for 120. So the cube root of 8 times 15. Again, I can break this up and say, well, what's the cube root of 8? And what's the cube root of 15? Well, the cube root of 8 is 2, because 2 times 2 times 2 is 8. So 2. And the cube root of 15 is just going to remain some irrational number, so I just keep it as a radical. Okay, hopefully you kind of remember how to do that. So then I'm going to take a quick look at how to do this now once we start looking at variables. Best way to do this is, let's just break this up. So I'm going to say, well, here's the square root of 48, and here's the square root of y to the power of 5. So let's just look at this first of all, 48. I know that the highest factor, or the highest perfect square that can go into 48 is 16. 16 times 3 is 48. So I would just break this up into 16 times root 3, which is 4 root 3. So that's going to be the numerical portion of this. Now I'll do the same thing with my variables, y to the 5. Now, because we're taking the square root, what we're trying to do is make as many groups of 2 as possible. So what I can do for myself is I can say, well, to make 5, I would have 1 group of 2, 2 group of 2s, and just 1, right? Because 2 plus 2 plus 1 equals 5. We have to remember our exponent laws there. Well, what's the square root of, and then if I break this up, square root of y squared times the square root of y squared times the square root of y. What's the square root of y squared? Y. What's the square root of y squared? Y. What's the square root of y? Well, that would just stay as irrational. And so now I can kind of simplify these to add those together. So y2 and the square root of y. So really what I want to do in the end is combine those together. So my coefficients come together as 4y, and my radicals come together as the square root of 3y. Sorry, y squared up front. E is the fourth root of c to the power of 9. Now, in order to take something out here, I'm looking for groups of 4. So if I look at this, I'm going to say I'm looking for groups of 4. So this would be c to the 4 times c to the 4 times c to the 1, right? Because 4 plus 1 is going to give me 9. And so I could break this up, the square root of c to the 4, the fourth root of c to the 4 times the fourth root of c. Well, the fourth root of c to the 4 is just going to give me c. The fourth root of c to the 4 gives me c, and the fourth root of c would just stay as that irrational number. So I would combine these using my exponent laws to give me c squared and the fourth root of c. I'm going to ignore that one. But the answer, if you're curious, is 4x cubed 5xy squared. And there's written notes or how to solve that on my diagram, on my note package. Okay, last part we'll do quickly. A little bit of an extension, maybe you looked at this, kind of depending on who your teacher was, is the difference between like and unlike radicals. Kind of similar to like and unlike polynomials in a way. So radicals with the same index and the same radicand are considered like radicals. So for example, like radicals would be 3 root 5 and 7 cube root 5, right? Same index, same radicand. The coefficient out front doesn't matter. Another example would be like the square root of 4 and let's say the negative square root of 12. Well, the square root of 4, the index is 2. What the heck did I do? Another example would be like the square root of 3 and the negative square root of 3. Index in both of those is 2, and the radicand is 3, so that makes them like radicals. Another example would be like the fourth root of 2x cubed and 5 times the fourth root of 2x cubed. Okay, my index is the same and my radicand is the same. So let's look at a few examples of unlike radicals. So if I had like the cube root of 4 and the cube root of 7, those are considered unlike radicals. They have the same index, but the radicands are different. So that makes them unlike radicals. If I had, let's say, the cube root of 7x and the square root of 7x, those are unlike radicals because their indexes are not the same. Their radicands are the same, but their index aren't the same. So they would be considered unlike. Another one would be like, let's say, the fourth root of 5y and the fourth root of 5xy. My indexes are the same, but my radicands are not identical, so those would be considered unlike radicals. So, like radicals can be combined together in the same way like terms are combined. So, for example, when I'm talking about polynomials, like if I have 2x cubed plus 9x cubed, well, I just add those together. So my coefficients come together, so that would be 11, and that just stays as x cubed. Here, what I would do is look for, so if I'm asked to simplify this big long thing here, what I would do is look for like terms. So the same index and the same radicand. My coefficient up front doesn't matter. So looking for like terms, 3 root 5 is similar to negative 12 root 5, and it's also similar to the square root of 5. So all I would do is add all of those together. So 3 minus 12 plus 1, adding all those together, I'm going to get negative 8 root 5. So the coefficients just come together, and my radicand stays the same, or my radical stays the same way that happens with our polynomials. I would also combine my root 7. So plus root 7 plus 4 root 7. So I just add my coefficients together. So plus 5, and then root 7 would just stay as is. So there's my final answer. I could always check that on my calculator, right? I write this whole thing in on my calculator, I write this whole thing in on my calculator, and I should get the same answer. Okay, so coefficients just get added or subtracted, and the radical, or the radicands, and the radicals will stay the same. All right, let's look at a few harder questions then. So it says simplify the following radicals. Root 50 plus 3 root 2. Looking at those aren't like terms, but they're saying like you can probably simplify this somehow. So what I want to do is I want to take this and I want to try and get it to be the same radicand. I want the radicand to be 2. Well, if I think about that then, 25 times 2 is equal to 50. So when I take the square root of each of those, that would become 5 root 2 plus 3 root 2. So I can change my mixed radical, or sorry, change my entire radical into a mixed radical. Then if the radicands are the same, all I do is add my coefficients together, and the radical will stay the same, 8 root 2. And that's a pretty easy one to verify on my calculator if I put both of those in. So I'll just show you. Square root of 50. Oops, delete. Got to make sure you move outside. If you have an older calculator and you're trying to verify, you have to use a whole bunch of brackets. 3 times the square root of 2. So that's 11.3. And my final answer there was 8 root 2. So I get the same irrational number. So that means that I have simplified correctly. Okay, let's take a look at C. So I have 4 square root of 4C minus 4, 9C. So a little bit ugly, but I want to try and simplify this because right now I don't really have like terms, but it looks like maybe I could get there. Well, if I break this up, the square root of 4 times the square root of C, well, the square root of 4 is 2 root C. So that's this one. Minus 4 times, well, again, if I could break this up, the square root of 9 times the square root of C, and the square root of 9 is 3. So minus 4 times 3 times root C. So I'll just simplify that second term. So minus 12 root C. And now I have like terms. Same index, same radicand. So I add or subtract those coefficients. So 2 minus 12 is going to give me negative 10. And the radical will stay the same. I could check that one by graphing if I really wanted to. They should give me the same graph. Or I could just substitute an arbitrary value in for C. Do not use 0 if you're substituting in. Do not use 1. I'd probably use maybe like a 5 or a 10. Should work. All right, last one is a little bit more complicated. So let's try and simplify this as much as I can. So here I have negative 27. I'm not going to read that out. Anyways, you can see the question. And it says simplify this. So what I would do is I would say, well, what's the lowest radicand here? I have a 5 right here. So I have a square root of 5. That can't get any lower. Can't be simplified any further. Can any of these terms work so I would have the same radicand? Well, 27 isn't divisible by 5, so that's not going to get to be the same radicand at any point. 12 is also not divisible by 5, so that's not going to be the same radicand at any point. But 80 could be divisible by 16. So 16 times 5 is actually equal to 80. And so that would become minus 4 root 5. Okay, so those terms could be simplified to give me 3 minus 4 is a negative 1 root 5. Whether you put that negative 1 out front or not, it's up to you. But then I got to look at these other two terms here. I have this one, and maybe they can be combined, maybe they can't. But I want to try and simplify them. So because this number is smaller, I'm just going to deal with that first. So minus 2 root 12. And I know that 12 can be broken into 4 times 3. 4 is the only perfect number of the index. 2 times 4 root 3, so minus 2 times 2 root 3, because that's what this would be equivalent to, 2 root 3. And then I'll simplify that, minus 4 root 3. Now I have the negative square root of 27, and I want to see if it's divisible by 3, because I want that radicand to be equivalent. So what times 27, or what times 3 is going to give me 27? Well, 9 times 3. And so if I break that up, the square root of 9 is 3 root 3. And because the 3 would come out front, it just gets times by that negative number. So I'll bring that down. And now these are like terms, so I would simplify them. Negative root 3 minus 4 root 3, so combine those coefficients. Negative 7 root 3, and this would just come down, the square root of 5, the negative square root of 5. That would be my final answer. Again, I could always verify that on my calculator if I chose to. Okay, so I know that's a pretty big lesson. Sorry for kind of throwing that all together in long form. I put up the homework book, so there's some homework. Homework 1 is working with radicals. It's about 3 pages long, or 4 pages long. I wouldn't necessarily, obviously, do every question. Try 2, 3, 4. If you're getting them all right, that's fine. Just go on to the next one. But if you are stuck and you just can't get a few questions right, email me and maybe I can help you somehow. Maybe we can do a Zoom session or something. So the questions are there, and the worked answers are all photocopied and online, so you can make sure that you're checking your work. There will probably be a quiz in the next coming day or so. Okay? All right, thanks for listening.